So that was the motor effect, creating movement from an electric current. We can turn the motor effect on its head if we move a wire in a magnetic field. This induces a potential difference or voltage in the wire, which can cause a current to flow. This is called electromagnetic induction. With a single piece of wire, the current is very tiny. If I coil up the wire so that more turns are in the field, it induces a larger voltage and a slightly larger current will flow, which you can now see on the meter. If I use a bigger magnet, that will also induce a bigger voltage and cause a larger current. With even more turns of wire, I get an even bigger voltage and an even larger current. So let's use an even bigger coil with even more turns and a smaller magnet. When I move the coil towards the magnet, the current flows one way. When I move the coil away from the magnet, the voltage is induced in the opposite direction and the current flows the other way. When the coil is stationary, no voltage is induced and no current flows. It doesn't matter whether it's the coil that's moving or the magnet. And if I turn the magnet round the other way, the voltage is induced in the opposite direction and the current flows the other way. This is called electromagnetic induction. I can even use an electromagnet. If I switch the electromagnet on and off near the coil, I also induce a voltage and a current flows. But the voltage is only induced in the coil while the current is changing. So instead of a battery, I can use an alternating current power supply. And you can see the needle is vibrating backwards and forwards, which shows that an alternating voltage is being induced, causing an alternating current in the coil. This gives us the principle of the transformer. If I pass an alternating current through a primary coil and I place it near to a secondary coil, the alternating current in the primary coil produces an alternating magnetic field in the core. The alternating magnetic field induces an alternating voltage in the secondary coil, and that produces a current flowing in the circuit. This is also the principle for contactless charging of your phone. We use the principle of electromagnetic induction to produce an AC generator. This coil of wire turns inside a magnetic field. These are slip rings, which are sliding contacts which make connection to the coil so that it can turn. As I turn the coil, first it faces one way, then it faces the other way, then the other, and so on in the magnetic field, which means it produces an alternating voltage, and that will drive an alternating current around the circuit. As I turn the handle, the generator produces a voltage. As I turn it faster, the voltage increases and the lamp gets brighter. So that was producing alternating current. If I plotted a graph of voltage against time, it would look like this. If I turn the handle faster, the frequency would increase and so would the voltage. If we use a light emitting diode as our indicator, we can show that we are producing alternating current because the diode only lights up in one direction and so it flickers. However, we can also use the principles of the DC motor to switch the current direction every half a turn to produce direct current. We use the split ring commutator. When we do this, instead of calling it an AC generator, we call it a dynamo and we get direct current. It will change the graph, which would look like this, into one which looks like this. We've changed from an alternating voltage to a direct voltage. It's not a constant voltage like a battery, but it is all in one direction. If I use my LED on the DC output terminals, I can show that we're producing direct current because the diode will only light up in one direction, but not the other way.